Okay. So we were saying that the next step, okay? So first we computed this element, okay? Now, if you move to, we were talking about this one, okay? This term should be equal to A21, but here because my matrix is symmetric, A21 is equal to A12, okay? And how can I get it? I just get it from multiplying, okay, the second row because it's A21 and it results from the multiplication of the second row with the first column. So to obtain it, I should do U12 times U11 plus U22 times 0 plus 0 times 0. I get the following element. So now I can say that from comparing the two matrices, that U11, U12 should be equal to A21, but A21 is equal to A12 because of symmetry of the matrix. Okay? Now, I can proceed to find all other elements. For example, if I consider this element, how can I get it? This is the result of multiplying the third row by the second column. Okay, because this term is A32, which will be equal to A23. Okay, because the matrix is symmetric. So I have, to get it, I just have to do U13 times U12 plus U23 times U22 plus U33 times 0. So I will get U13 U12 plus U23 U22. Another term, for example, how to get this one? This one is A33. So I get it from multiplying the third row by the third column. So I get U13 times U13, which is U13 square, plus U23 times U23, which is U23 square, plus U33 times U33, which is U33 square. So now I need to solve for 6 unknowns, which are U11, U12, U13, U22, U23, and U33. To be able to solve for these coefficients, all I have to do is to compare. I will compare the results of the multiplication with matrix A. So I will start with U11, this term. By comparison, this term, U11 squared, should be equal to A11. So the first element is now determined. U11 is equal to radical of A11. Once I got U11, I can move now to do the following comparison. I compare the second term in the first column. So U11, U12 is equal to A12. And since I calculated already U11 from the previous step, so I can write U12 as A12 over U11. So now I can calculate U12. Now I move to the third element of the first column. U11, U13 is equal to A13. So I can replace U13 by A13 over U11. So already I am done with the first 3 unknowns. I still have only to compute the other 3. So now I move to this element here. Okay? I want to get U22. So I say that U11 times U22, okay, should be equal to which term? To this one, to A12. Okay? So this will allow me to calculate the value of U22. Or also I can find U22. Another way to find U22 is to use this equation. And here you have several possibilities. Because once you found already, and already from the previous steps, you find what is U11 and you found what is U12. So now to find U22, or you can use this term or you can use this one, both will lead to the same result. And if you use this one, you will get that U11, U22 is equal to A12. So you can write U22 as A12 over U11. So this is one possibility. Okay. The other possibility is to say I will find u22 from this equation. So if I want to do so, I can write that u1 2 square plus u22 square is equal now to a22. So now I can calculate a22 as a second method to calculate it is to say that u22 is equal to radical of a22 minus u12 square. Okay, and now I can proceed to calculate u23. Okay, if I want to calculate u23, then I will say that u13 times u12 plus u23 times u22 is equal to a23. And already from the previous step, I calculated already u12, and I calculated already u22 and u13. So the only unknown now will be u23. So I can get that u23 can be given from the following equation. It will be equal to a23 minus u1312 over u22. Okay, and the only element which will remain to find is u33. To get u33 also I have several possibilities. Okay, I can compare u11 u13 should be equal to a13. So this is one possibility. I can also calculate it, sorry, u33, you can calculate it from here. u13 because it's already calculated from the previous step. Okay, you will get exactly the same result. So you just need to find u33. The only element involving u33 is this one. So you will use the following equation. You have that the following term should be equal to a33. So now already we have a u13 and already we have u23. So we can say that u33 is radical a33 minus u13 square minus u23. It might seem for you that it is a little bit complex, but once you have these equations, it will be very easy. So now you don't have to do this every time. You just apply these relations. These six equations, you substitute just a coefficients a by their values, and once you find u, you can substitute here also. So you can get all these factors in a very simple way, which is much faster than performing the LU factorization. Okay, so for example, here, let us practice, let us use Cholesky factorization for the below A matrix. So if I give you the below A matrix and I tell you to factorize it into a lower and upper matrix, you have several possibilities. You can do Gauss elimination and you directly find L and U. Okay, you can do here's the idea, and Gauss elimination, here's technique to find LU factorization, because we do elimination and then we fill the lower matrix by the factors used in the Gauss elimination. Second possibility, okay, is to verify if this matrix is positive, definite, and symmetric. So then no need to use LU factorization because Cholesky is much easier. So here, for example, if I give you this matrix, if I tell you use Cholesky to factorize it, you can be sure that the two conditions of symmetry and positive definite are satisfied. Okay? If I don't tell you, if I just tell you verify if this matrix can be factorized using Cholesky method, then you should verify that it's symmetric and it is positive definite. Okay? If not, if I don't tell you to verify this, then you can directly proceed, because I told you here use Cholesky factorization for the below matrix. This means that of course this matrix should be symmetric and should be positive definite. So here, just to practice, let us make sure of these two properties. So the first thing to do is to make sure that it's symmetric. You can simply verify that it's symmetric, because first, if you take the diagonal, you have your elements are in symmetrical with respect to the diagonal. Okay. The second way to verify symmetry you have that it's a square matrix 3 by 3, and if you calculate the transpose of A, okay, it will be equal to A, because the transpose of A, so this is 9 minus 6, 12. It will be 9 minus 6, 12. Also, minus 6, 5 minus 9 will become minus 6, 5 minus 9. And 12 minus 9, 21 is 12 minus 9, 21. So it's verified, okay? It's a symmetric matrix. Now, if I want to use Cholesky factorization, I will use the following rules to come up with my upper matrix. Okay. First, the first term of my upper matrix U11 is just radical of A11, so it's radical 9, so it's equal to 3. I am done with the first element. The second element is A12 over U11. A12 is minus 6 over U11, which is 3. So minus 6 over 3 will give me minus 2. So I put here minus 2. Now, U13 is A13 over U11. This is A13, 12 over U11, which is 3. 12 over 3 will give me 4. Now, I still have 3 other elements to compute. U22. U22 is radical A22. A22 is 5 minus U12 squared. Since U12 is equal to, was found to be equal to minus 2, then it's minus 2 squared. So it's 5 minus 4. So it's radical of 1, which is 1. So I can deduce that U22 is 1. Now for U23, it's equal to A23. A23 is minus 9 minus U13. U13 is 4 times U12. U12 is minus 2 over U22, okay, which is 1. So I get minus 9 plus 8 over 1, which is minus 1. So this is U23. And finally, for U33, to get U33, I do radical. A33 is 21. I replace U13 by 4, so minus 4 squared. U23 is minus 1, so minus 1. So I do now radical of 21 minus 16 minus 1, so it's radical of 4, which is 2. So the final term U33 is 2. And I am done. Try to do it using LU factorization. It will take much more time because you have a much higher number of operations to perform. So now, the only difference is here, how to factorize. Once you factorize using Cholesky factorization, you will get A in the form of L times U. But what will be L here? L will just be the transpose of U. Okay, because Cholesky factorization will tell us that if a matrix is symmetric and positive definite, I can write it in the form of the transpose of an upper matrix times the upper matrix. So now you can say that the factorization of A, one possibility of factorizing A in a lower and upper matrix will be as follows. So now I will take the transpose of this matrix. So the first row will become the first column, 3 minus 2, 4. The second row will become the second column, 0, 1, minus 1. And the third row will become the third column, 0, 0, 2. This is my lower matrix. And my upper matrix is the matrix as it is, here, 3, minus 2, 4, 0, 1, minus 1, and 0, 0, 2. Now, to proceed to solve for, if I give you A x times x equal B, you proceed with forward substitution, then backward substitution, since already you have the lower and upper matrices. Any question on this?
دكتور
Yes.
بس بدنا نبروف that it's positive definite matrix
Yes.
الاكس الماتريكس بناخدها unknowns ولا فينا ناخد 1 2 3
ايه لا اكيد unknowns حسن، لانه اذا بتاخد particular case مين بياكد لك انه for any other vector x ما تطلع negative مثلا؟ whenever they tell you to prove it's a definite positive matrix بدك تاخد x any possible vector الا zero، يعني لانه اذا x بيكون zero هيطلع لي equal zero. So any x different than zero يعني بدي احط variables a b c. اذا مثلا كان عندي 4 by 4 بيصيروا a b c d.
يس دكتور. والدكتور بس لاعمل بروف انها سيمتريك فيني
إيه.
بس ورجيهم انه هن ميرور بلا ما اطلع
فيك
الترانسبوز.
مظبوط، فيك تورجيهم انه mirror او فيك تعمل الترانسبوز.
يس ثانك يو دكتور.
دكتور
نعم.
هلا نحن الاليو بنستعملها بدل الجاس اذا كان في اكثر من بي بدنا نغيره.
مظبوط.
هلا بالتشولسكي لما نحن نستخدمها هي بس لما نلاحظ انه هي حتطول الاليو.
هلا ليك التشولسكي حتى فيك تعملها لو جاس لو عندك فيكتور بي واحد لانه كثير سريعه، يعني دغري فيك.
يس
ما هي كانت الديزادفانتج قبل انه بدها وقت الاليو، بدي ارجع اعمل فورورد وباكورد سبستيوشن، بس ما هون الاليو دغري بتجيبهم ساعتها الفورورد والباكورد. يعني مزبوط انه اذا الفرق عن جاس انه زياده عندي الفورورد سبستيوشن، بس برضه وفرت كثير اوبريشن تبع الجاس. يعني الفورورد اليمينيشن تبع جاس بدها وقت صح؟
يس مزبوط.
انت الاليو هون دغري بتلاقيهم، يعني التشولسكي احسن من الجاس لو كان عندي 1 فاكتور،
يس
بينما الاليو فاكتورايزيشن منا احسن من جاس اذا بس عندي بي فاكتور واحد.
يس وهون انا بجيب اليو منه دغري بجيب اليو تي يعني
اكزاكت.
وبس بعمل السبستيوشن.
مزبوط. فلو بدي اعمل باكورد وفورورد بعدين سبستيوشن، ما الفورورد سبستيوشن ما بدها كثير وقت دغري بعملها.
يس ثانك يو دكتور.
Welcome. Any other question? Okay. So this is the end of chapter 10. Okay, we are done with chapter 10, and now we will be ready to start a new chapter. This is the final chapter للإكزام. يعني للإكزام you have 9, 10 and 11 because they are related to each other. يعني you will need information مثل ما شفنا استعملنا chapter 9 ب chapter 10, and now we will also use these concepts in chapter 11. So first, this chapter is called matrix inverse and condition. In this chapter, we will mainly introduce how to find the matrix inverse and how we can use it, how it can help us into knowing the condition of a matrix and into knowing how a variation of the force can affect the variation of the variables of my system. So at the end of this chapter, you will be able to compute matrix inverse. You will be able to compute condition number and learn what is its importance in assessing ground of error. And you will appreciate the importance of the inverse matrix in providing insight to engineering problems. So let us start first with the general idea of this chapter. We will go back to the same example. We consider several masses with springs that are connecting them, and they are subjected to external forces. And we have seen that such system can be written as the product of a matrix K, which is depending on the properties of the system, which are the stiffness of the springs relating the masses, times the displacement vector x, which will be our unknowns to find, equals to the force vector x. And we said in the first chapter that if we have a high number of masses with a lot of springs, then we will have a system of linear equations. And we should develop techniques to solve it. The first chapter 9 introduced gas elimination methods. Then in chapter and Kramer's technique, but we said that Kramer is not very efficient when we have a lot of, when the dimension is high. So in chapter 10, we then said that what if I'm keeping the same system, but I'm changing vector B? I need to come up with an efficient method to not have to do cost elimination every time, and we come up with the LU factorization method, and also we come up with Cholesky method in case the matrix was symmetric and positive definite. Now, what will happen, for example, if I want to see the sensitivity of variation of my displacement with a certain force? So, for example, if I tell you I will double F4 while keeping, so of course I'm working on the same system, so okay, it will remain unchanged, but just I'm doubling F4, and I want to see its effect on on just X1. If I use the previous methods, I should, to find the effect on x1, I should solve for all of displacement, x1, x2, x3, x4, and x5, etc., depending on the number of variables, because my equations were coupled. So what will be the strategy if I just want to see what is the effect of f4 only on x1 and not on all vectors? The method will be to decouple the solution. How this is possible? This chapter will give us solution for this. How we can just see the effect. If I vary just one force, how it will affect a certain displacement. This will be introduced in this chapter. Okay. So this is the overall idea, and now we will start to see how we can achieve our objective. We will see that matrix inverse will allow us to have further insight into complex and coupled problems. This is why the first step in this chapter will be to introduce how to calculate the inverse of a matrix. So first, what is the inverse of a matrix? For a square matrix, the inverse is such that A minus 1 times A will equal to the identity matrix. Okay? So this is the definition of the inverse of a matrix. It's in a way that A minus 1 times A will be equal to the identity matrix. And by identity matrix, we mean the matrix with 0 elements everywhere and 1 element on the diagonal. So if we are talking about a 3 by 3 matrix, this is the identity matrix. 1, 0, 0, 0, 1, 0, and 0, 0, 1. Now, it is always possible to find an inverse? No. So you should know that it's not always possible to compute the inverse of a matrix. And why? Because if the determinant of a matrix is 0, we cannot find its inverse. To understand more this, I will give you analogy in numbers. In numbers, for example, the inverse of 3 is 1 over 3. So 3 times 1 over 3 is equal to 1. Okay, so here's the equivalent of, if we do the analogy with the matrices, the equivalent of 1 in matrices is the identity matrix. The equivalent here of 3 is, let's say, A, and the equivalent of A minus 1 is 1 over 3, for example. Now, if I give you 0, can you give me the inverse of 0? No, because you don't have 1 over 0. So it will be infinity, and it will not be a definite thing. So this is why we say that we cannot always compute the inverse of a matrix, because, and the criterion here, the criterion in matrices is that if the determinant of a matrix is 0, I cannot define an inverse form. Okay. Now, how we can calculate the inverse of a matrix? This is a little bit also complex. So let us try to come up with a definition to find the matrix. To find the inverse of the matrix, we will start from the definition that A times A minus 1 is equal to the identity matrix. So first, since matrix A, this is a general form of it, A11, A12, A13, A21, A22, A23, A31, A32, A33. Now, to define A minus 1, we don't know it. So we will say that all the elements will be unknown. So how many unknowns do I have? 9. If I take a 3 by 3 matrix A, then I will have 9 elements of A and 9 elements of A minus 1. And since A minus 1 is unknown, then I have 9 unknowns to find. To find these 9 unknowns, the methodology, the first method that come to my mind is to say I will start with the definition of the inverse. From definition of inverse, I have A times A minus 1 is equal to identity matrix. And here, you can commute. This is a particular case where you can commute matrices. So A minus 1 times A is equal to A times A minus 1 is equal to the identity matrix. Okay. So now if I apply this rule, I will come up with the following result. So if I just put A times A minus 1 equals to the identity matrix, and I will do the expansion, I will get the first element of my expansion will be obtained from multiplying the first row of A by the first column of A minus 1. So I have A11 times B11 plus A12 times B21 plus A13 times B31 will give me the first element. And by comparison, this should be equal to 1. So if you want, this will be your first equation. This is equal to 1. The second element will be obtained by now multiplying the first row element with the second column element. So I will get A11 times V12 plus A12 times V22 plus A13 times V32 equals to 0. Okay, so this element should be equal to 0. This is my second equation. Similarly, for the third element now, what will be the third equation involved? I will have A11 times V13 plus A12 times V23 plus A13 times V33. This should be equal to A13, which is 0. And I will repeat the same procedure to do the, so let us take any arbitrary term now. How to get this term? This term is equal to, it's in the third row, second column, so it should be equal to the third element of identity matrix. So identity matrix A32. A32 is 0. Okay, and I can compute it from multiplying the third row of the first matrix by the second column of the second one. So this term is obtained by multiplying this row, which is the third row of matrix 1, times the second column of matrix 2. So as you can see, the result will be A31 times V12 plus A32 times V22 plus A33 times V32, which what I wrote here, equals to the element 32 of the identity matrix, which is 0. So this is equal to 0. So when you perform the full expansion, you will get 9 equations, because each term here, this term is equal to this one. So this is your first equation. This is equation 1. Equation 2 is that this term is equal to 0. Equation 3 is that this term is equal to 0. The fourth equation is that this equation is 0. The fifth equation is that this equation is equal to 1. And the sixth equation will be that this equation is equal to 0. Now, seventh equation, this term is equal to 0. Eighth equation, this term is equal to 0. And the final, the equation number 9 is that this term is equal to 1. So I end up with 9 equations with 9 unknowns, which is really hard to compute. I can do Gauss elimination, for example. So if I rewrite my 9 equations with 9 unknowns in matrix form, I will get here a 9 by 9 matrix. And I will have to solve for this linear system of equations. The first possibility is Kramer's rule, which is not recommended. A second possibility is Gaussian. Here Gaussian is better than LU factorization, because here I just have one column, one B element. Okay, so no need to do LU factorization. I can do Gauss elimination, but still Gauss is also very, yeah, it's very complex here because I have 9 by 9. So I will need a lot of time to perform forward elimination for all of these terms. Yeah, I should eliminate these, all of these terms should be eliminated. Okay, so I will get, in order to get an upper triangular matrix here. Okay, I should eliminate all of these. This will take time. What is good here is that I have zeros, which will facilitate a little bit my operation, but still I need to do several steps for forward elimination. This is why we want to think about another strategy that make the calculation of the determinant, the calculation of the inverse of a matrix simpler. Okay, I want you to think about it a little bit, and we will continue this next time. Okay, any question on this? Okay, so I'll stop here to be with this with the other section in the same track. Okay, yeah, we continue tomorrow. Bye bye.